I guess already I have to thank all the other speakers on this session to pave the way literally for me, because I'm going to talk about these theta compounds which are glassy. But before that, I want to thank all my collaborators. A lot of work I did together with Vlad and his student Sami. Simone and Arnaud, we have a paper together which I largely will discuss. And I discussed a lot of work together with Zoran Usinov, Miguel Ortuño, and Leon Balent. So when you think about a glass, and not what you put into a glass, but the properties of the glass itself, I tend to think about it as having four characteristic features which all glasses have. The first one would be that glasses have slow dynamics in a sense. Even can be so slow that they have memory. So that will be the number one. Number two is glasses often have a soft excitation gap. So certain class of excitations, there is zero density of states at zero energy, but there's always a finite at infinitesimal energy. So that's what constitutes a soft gap. Often glasses, and that's the third one, have short-range correlations of some sense. We've seen that in the previous talk. And the fourth one, and that's a more theoretical one, is that glasses are characterized by a very wild and rugged energy landscape. And these are the four things that will come back throughout my talk when I discuss first a little bit of the experiments, but that has been largely done, so I can rush through that, I guess. But I'm a theorist, so I'll get to the theory of that later. So theoretically speaking, what a glass actually is, it's one of it's a phase of matter, but not one of the common ones like liquids or gases or solids, because it's a non-equilibrium one. And it arises naturally if you have a first-order phase transition, as Pierre Monceau already mentioned. So I always like to just briefly remind it, if in a nice entropy temperature phase diagram, if you just have a system which is liquid at high temperatures and entropy decreases rapidly with temperature, there's at some point a first-order phase transition to the solid phase, which has a slower entropy versus temperature rate. But you can supercool it because the liquid is metastable. So if you just imagine you can follow that entropy decrease that a liquid does, at some point you reach a temperature. Oh, I have a pointer. Yeah. At some point you reach a temperature where there would be a contradiction. In that case, the liquid would have a lower entropy than the solid, which is called the Kautzmann paradox. It's not possible, liquids having lower entropy than solids. So what the system actually does is before you reach the Kautzmann temperature, you have a temperature in which all the system gets arrested. It slows down and it gets frozen in some disordered state. So that would be the glass state. So normally that is for generic systems. The question is, can you have such a system for electrons? So when you talk about normal phases of matter, gas, liquid, etc., you have that too for electrons. So there's the electron gas, which is just a free electron gas. Electron liquid would be a Fermi liquid, so dressed with excitations, but still pretty free. You have electron solids. The Wigner crystal was mentioned yesterday by Simone. You have charge order, which has been discussed extensively this morning. When we think about electron glasses, we usually talk about them in terms of disorder. And disorder, what I mean is not that the system itself is, that the glass is amorphous or something. No, what I mean with disorder is there's quench disorder. In your Hamiltonian, there are random terms. That's the way how we usually think about glasses. So the case where you don't have interactions, we call that the Anderson insulator. We have cases where you include weak short-range interactions. That's often referred as many-body localization. If you have very strong but long-range interaction, that's often referred as the Coulomb glass. But in all these cases, you have some random energies, random terms in your Hamiltonian. But that's different from what I just said about the supercooled liquid, because in supercooled liquids like window glass, there's no random term in your Hamiltonian of window glass. So the question is, can you have a supercool electron glass? And I guess it's already mentioned in the previous talk. So I like the name Supercool. So the supercool electron glass that I like to talk about, and mainly based on the experiments done by Kagawa and Kanoda and others, is this theta compound. Well, I'm not going to review again what the theta compound is, but the baseline is you have these triangular lattice of these BED TTF molecules with a quarter filling, which means 1 electron per 2 molecules. So from now on, I will drop the spin. So you can say quarter filled, or you can also say half filled spinless electrons. And these half filled systems, also been discussed yesterday by Simone, they are a certain type of frustration. It's similar to spin frustration on an icing system, but now it's charge frustration with charge-rich and charge-poor sites. It's a bad metal conference, so just briefly I have to show conductivity measurements. I would definitely classify this as a bad metal for starters, that it's pretty insulating for a conductor. Yeah, Pierre mentioned this. If you slow cool the system, you get into, this is a rubidium zinc, by the way, you get into a stripe-ordered state. And if you fast cool, you can avoid it, and you get this supercooled electron liquid. It's not a glass yet. Just like if you fast cool silicon dioxide below its charge ordering transition, it's first a supercool liquid. You have to really get to a point where the dynamics are so slow that you are really out of equilibrium before you can call it a glass. So to do that, you have to study the dynamics. And there's these nice experiments from the paper I mentioned before by Kagawa, where they studied the typical dynamical timescale of these systems. So this is a typical way to plot that. You saw it also in the previous talk. This is 1 over temperature. So on the right side, that's high temperature. On the right side it's low temperature, and on the left side it's high temperature. And this is a logarithmic scale of the typical time scale. At high temperatures, what they did is they measured the noise in the resistivity data. And typically you have some 1 over F noise, but on top of that you see a specific frequency where you have a peak, an extra. So there you can extract from the noise spectrum a typical frequency where you have dynamics associated with charge. At low temperatures, what you can do is you can rapidly cool to that point, because we need to rapid cool to avoid the charge ordering transition. And then you can wait how long it takes the system to equilibrate. And now there's one very important thing that you have to say. This is in seconds, but the 10 log of seconds. So this region is like milliseconds, which is already pretty slow for electrons, because electrons usually do stuff on the order of nanoseconds or faster. 10 to the power 4 seconds, that's about a week. So you already see that this is around 100 Kelvin. Around 100 Kelvin, dynamics are so slow that it takes longer than a week to equilibrate. And that is what I would call definitely glassy, longer than a week. Also because it takes longer to do experiments. It's impossible to do experiments longer than a week. The straight line that you see here, it's the Arrhenius law, so you can, that's why the plot is chosen in such a way that you have a straight line associated with this activated energy. Arrhenius was a chemist, actually. He won a Nobel Prize for deducing that chemical reactions change, the reaction rate changes in this fashion, where this delta, he said it's the activation energy. For chemical reactions, it's a very natural thing. You need an activation energy before you can go to the other side of your chemical reaction. In this case, the plot, this can be fitted, the data, with like a 2600 Kelvin activation energy. But the question is, why would glasses care about that? So there's no chemical reaction going on here. And the natural way to think about it is this rugged energy landscape, one of the 4 properties that I told you before. So this is a typical way that people think about the energy landscape of a glass. And this is not in the disordered sense like in the Anderson insulator, where the horizontal axis is space. No, this is in phase space, or configuration space. So there are different configurations. There's the crystal phase, which to the theta compounds would correspond to the stripe-ordered phase. And there are a lot of local minima. And classically, this makes sense, because then in order to go from one minimum to another minimum, you have to overcome some activation energy barrier, so that it's natural that these rugged landscape, the typical height of the barriers defines the activation energy, and thus you get Arrhenius law behavior for a glass. But for electrons, that actually doesn't make sense, because the electrons can tunnel their quantum mechanically. You can also, even at 0 temperature, electrons can go through any kind of barrier. You don't need thermal activation, you have quantum tunneling. So you need more in order to get, you need more than just a rugged energy landscape to get electrons to behave glassy. You need frustration, and we saw we have that, because you have a triangular lattice with these charge frustration. So let's quickly review what also was said yesterday. If you just take this, or even in the previous talk as well, you take the extended Hubbard model of these electrons, which means next to the on-site repulsion, you also have nearest neighbor repulsion, which is a generic form like this, but then this Vij would only be nearest neighbor. But this is a hugely degenerate system. So usually you would say, oh, glasses, that's nice. You want some huge degeneracy in the number of ground states. Explicitly, you have all these different kinds of stripe phases. You also have this 3 sublattice structure, which, if you include quantum corrections, would lead to this pinball liquid that Simone talked about yesterday, where you take one of the 3 sublattices filled, the other empty, and the third one you half fill that sublattice. So then you still have the right amount of filling. But they all have exactly the same energy, because you can count that for each, the average number of nearest neighbors is always 2 out of the 6. So you have 6 nearest neighbor sites, 2 of them are occupied for an occupied site. The problem with this is that these states are not metastable. You can always go from one state to the other without energy cost, so there's no barriers in between these states. Well, in the stripe phase there is, but in these, which are exponentially many of them, you don't have barriers in between them. And if you don't have barriers, you still cannot get anything glassy. So we need to introduce more frustration. So the model that we suggest is that you have to take into account the fact that these guys are actually electrons, so they have long-range Coulomb interactions. And if they have long-range Coulomb interactions, you actually introduce the kind of frustration that you need in order to get these glassy physics. So with a long-range Coulomb interaction, all these different states, which were exactly degenerate in the case of just nearest neighbor repulsion, become, well, the degeneracy is lifted. So actually the stripe phase is now the lowest in energy, which is something which makes sense. At least you want it in a sort of phenomenological way, because the rubidium zinc has a stripe-ordered ground state. So that's kind of nice. The point is that if you then look at all these states that are different structures and look at their energies and their barriers, it turns out that you now have exponentially many metastable states, in the sense that they're local energy minima and that there's a barrier to get from one state to the other. It's easy said, but when I say that, oh, by the way, I should mention that the idea that you get long-range interaction with stripes leads to glassiness, that's actually, it's not ours. I think it's introduced first by Jörg Schmalian. If I say metastable, yeah, it's not a well-defined concept to be metastable. So there's various ways that you can talk about metastability, because there's various ways that I can put, say, a metric on my configuration space. What does it mean for 2 configurations to be close to another? So the most natural, or in any case, the most simple way to talk about it is to say, if I have a configuration, another configuration is close, we're just moving one particle. So the question of metastability then reduces to the question, if I have my state, is it stable against any one particle move? And the way to do that is to say, well, I will get back to this equation in more detail later. You have to say the energy difference, if I move a particle from site J to site I, then there's also this interaction factor, which you have to take into account. But the total energy change, if I move my particle from I to J, must be positive. So that's the natural definition of a metastable state. And then you can just count. You can actually just numerically, you take your system, you can put it on a lattice, we already have a lattice, we compute it on a computer, and we just count the number of metastable states, and you indeed find you have exponentially many of the metastable states, and they have these horribly complicated looking structures like this. There are exponentially many, but the interesting thing about these systems is that you don't need to care about exponentially many, because only a small set of these metastable configurations are actually relevant for the physics of the system. The way that I do that is I take a high temperature, so random configuration, I fast cool my system, and we did it with Monte Carlo simulations, and then there's only actually a finite set, not an exponentially many, or not finite, but a less than exponentially many set of the metastable states are the ones that you actually reach. Most of the metastable states are in so distinct corner of your phase space that there's practically 0 probability that you end up with them if you start out with a random high energy state and then fast cool to them. There's a way we actually counted that. So what you can do is you can do literally what I just said, start with a random initial state, fast cool it, go to the lowest energy state, try to find the metastable state that corresponds to that, and then just simply count. And the fun thing is already if you take, say, a 36 by 36 lattice, which is pretty big, and you fast cool it, and you take, say, 1,000 initial random configurations, you already have doublings. You already have states which are, you find metastable states which occur more than once in the set of metastable states that you generate, which is impossible if you have an exponentially many of relevant metastable states. The funny thing about these relevant metastable states is also that they're all similar. So they have a higher energy than the ground state, but if you look at all their properties, like their energy, they become similar in the thermodynamic limit. So this is a distribution of energies of these metastable states that I found, and for larger and larger lattices, they just get peaked about a very specific energy, and they also have exactly the same charge correlations, et cetera, et cetera. So these metastable states, they're coined inherent states at some point by people. Those are the relevant ones. So not all of them, but there's a certain class of states that is relevant. So if we want to probe these relevant states, I already said we did Monte Carlo. Before I just did a variational one. Now I'm looking at what happens at finite temperature because I want to understand the type of data that came out of the experiments, which was this dynamical time scale. So briefly, I did Monte Carlo, just Metropolis. We have long-range interactions, which require some tricks because your computer is not infinite range. So you need to do a trick, which is called an Ewald summation, where you, if you want to know the interaction between, say, the green side and the blue side, you just say, well, I have the green side and the blue side, and I copy my lattice infinitely many times, and I just do the resummation numerically, and then you get this horrible equation that this is actually the interaction that you have to put into your computer. So at finite temperature, the kinetic energy is simulated by just the hopping. So it's strictly speaking a classical model.
It's a classical model.
Yes, yes. So it's a classical model. Yes, exactly.
But by itself, the Hamiltonian is not.
Yes, exactly. Yeah. So there's actually, out of time, I didn't put that in, but what we did together with Simone and Erno, they actually did the exact diagonalization, and you can see that this stripe-ordered phase, which was the ground state, is actually stable in this long-range model with respect to introducing kinetic energy. So with that in mind, we thought, okay, from now on, we just do it classically. In these Monte Carlo simulations, the way we probe the dynamical timescale, which is the one that I wanted, is via the autocorrelation function, which is the correlation at a certain time, the configuration at a certain time correlated with the configuration at a later time. The two times that I put in here are first what I call the waiting time. So I start my simulation, I wait a certain time, I measure my correlation, and then I look at a time after my waiting time to see what the correlation between these two times is. If my system equilibrates, it should not depend on how far I am from the start of my simulation. So a system that equilibrates loses its depending on the waiting time. And then you have this single autocorrelation function, which depends on only one time, and that has an exponential tail. From that, you can get a dynamical timescale. And ta-da, this is the result. The Arrhenius law that we find, well, first of all, we find an Arrhenius law, and we found an Arrhenius law with the same slope, actually. So 0.2 times the nearest neighbor repulsion, where the nearest neighbor repulsion is, according to ab initio calculation, of an order of an electron volt. So this is pretty close to the 2600 Kelvin that they see in experiments. So this is still in the case where you can see equilibration. You can try to push this system that we have, try to push it to the state where there's completely non-equilibrium physics, completely non-equilibrium defined in the sense, like I said before, that dynamical timescales become so long that you don't want to wait all the time. It's a bit of a hand-waving definition of glassiness. But in practical sense, what you can do is you can look at temperatures below what we call the spinodal point, where there are two spinodal points. I think we have here the spinodal point where the solid phase and the liquid phase are both stable below that point. And then we actually see something nice, which is a scaling of the autocorrelation function with a specific power, which is a power half. So this is a phenomenon which is called sub-aging in Glassy physics, which is something what we see here in our Monte Carlo data. As far as I know, there's not really a good analytic theory of sub-aging scaling. So that's something that's still interesting to work on. The conductivity, which is another measure that I showed, we can also try to get the conductivity, which is more difficult to get out of these Monte Carlo simulations because didn't put any kinetic energy in it. But what we did is you can actually do a DMFT, but then the extended one, and the extended means you also include the long-range Coulomb interactions, because normal DMFT doesn't have this long-range Coulomb. If you want to introduce a force like that, that's where the word extended comes in. And the most important equation there is that you self-consistently solve the density-density correlations, where you just need to solve this parameter delta in the classical limit. So this is parameter delta. The point is that you do see this resistivity minimum or conductivity maximum that was mentioned in the previous talk as well, and a power law almost upturn in the conductivity, but it's only qualitative. We couldn't get any quantitative agreement with the organics using this EDMFT technique. We might get better results if we include the full kinetic terms, because what we did is it's sort of semi-classical solution and then did the inclusion of the kinetic energy perturbatively. But yeah, so this is still also work in ongoing progress, I guess.
So what exactly happened here? So you have still your classical objects, and now you look at
EDMFT. So you So I solved the classical model. From that, you get the density-density correlations.
Okay.
And from that, you can perturbatively, from that moment, you can say, well, if I have a very small t, very small hopping t, then I can derive a formal expression for how my conductivity looks in this very small t. And then what enters there is, of course, density-density correlations and density of states.
So you get the density-density correlator of this glass, and then you transport with the knowledge of this.
Yes, that's a point. Yeah, exactly. Sorry?
Right, so in order to have a small parameter, you have to balance T with another quantity carrier and some energy in.
Interaction energy.
Basically assume that there are always barriers.
Yeah, and well,
There's no resonances, no chemical states.
Yes, there's no resonances, or yeah, that's a very MBL word, I guess. But the small parameter is T over U, or T over V. Well, we do spinless, so there's not really a U. So the small parameter is T over V. And that's how you do the expansion for the conductivity. So this is just this expression for conductivity where you don't enter this hopping parameter. So this is just a proportionality. We just enter the density of states that you get out of this EDMFT. I can give you more details if you want. So I just mentioned density correlations, so I think it's also good to look at those. We saw in a previous talk that the Glassy phase has these short range. I call it short range, even though it went up to 100 angstrom, but it's not infinite range. So I still call it short range correlations at specific wave factors. And the interesting thing is, you also see like two competing peaks. So we have a triangular lattice, so the Brillouin zone is hexagonal. If you just take the long range interactions, only the long range interactions, you see a very sharp peak at the M point. And the M point is the one that corresponds to the stripe phase. If you also mix in a part of a short range component, which is measured by this parameter x, which includes the amount of short range one, you also see a peak appearing at the K point. The K point is the one that would be associated with the pinball liquid or the threefold structure that Simone talked about yesterday. So we also see that there's like there's competition in the correlation functions, in the density correlations, and you have them always short range. There's not much, there's no real charge order going on here. Yeah, so the fourth part that I mentioned in the introduction was the soft excitation gap. And for that, I just briefly review the idea from Coulomb gaps, which were the ones also were disordered classes with long-range interactions. Before, I'm going to tie up the idea of a soft excitation gap with the density correlations that I showed in the previous slide. So the energy to add or remove a particle in a disordered system is you have this on-site energy and you have this Coulomb energy. So you have to take into account that if I remove a particle or add a particle, it has this interaction with all the other particles that are already there. So the question that Efros and Shklovskii asked themselves is, what is the distribution of these energies in the ground state of this disordered system? So the main property of this ground state, they said, is it has a stability. If I move a particle, I have to change. I have to pay energy, and I gain energy. Pay energy on one side, I gain energy on the other side, and I have to subtract the fact that there was an interaction between the two sides that are included in my both terms. They called it the exciton term. So ground state naturally has this stability because it's stability to any kind of moves, the ground state. But I can just reshuffle this equation and saying, so that means that if I have states with this energy and if I have two states with different energies close to the Fermi level, they must be at least this distance apart. Which means that if I say that states with a very low energy, you can see if I put very small numbers here, they have to be very far apart, which suppresses the states close to the Fermi level. And this is what the Efros-Shklovskii gap says. Depending on the dimensionality, which naturally enters if you're going to translate distance into a density, the density of states must be less than some power law of the energy. So that's the case for these disordered Coulomb glasses. But if you just look back, well, this stability argument, it didn't require there was a ground state. It just required that it has to be metastable, like I said before. And you actually don't require, you just put in these energies here. You don't require in the argument that you have to put in the mu, the random potential. So you would expect that you have a Coulomb gap regardless of disorder, also in the system that we study, where you still have a Coulomb interaction, but no disorder. And that's the case. So I did some numerics. So these are the ones, these are a lot of different curves with a lot of different parameters. The baseline is there for different lattice sizes. And these two curves, or these two set of curves, are the ones where I have a lot of disorder. And you see that they're linear close to the Fermi level. Yes. These are the ones that we got from the model that we have without disorder, which still satisfies this Coulomb Efros-Shklovskii gap, but it's softer, or it's sorry, not softer. It's a stronger gap than we had for the disordered case. So I'll try to understand that in a way. In fact, we can plot it with this kind of exponential suppression close to the Fermi level. And the way that I want to think about that is I want to connect that to the correlations, because roughly in one sentence, and I'm going to put equations up after that sentence, the Efros-Shklovskii argument depends on long distance for small energies. It connects long distances with small energies. But you know, at long distances, you have this exponential tail of the density-density correlations. So that's what we know about long distances. So the idea is we have the density-density correlations. But I can also say, if I have my origin here and it's an empty site, what is the probability that I have at a site at distance r an electron? So that's naturally given by the density-density correlations. In this, you just have these factors half and stuff because of definitions. But you can also say, well, I have a local density of states, which I denote as G of R epsilon. And the chance that I have an electron, electrons have in this language, by definition, a negative energy, because they must be below the Fermi level. So the probability that I find an electron there is related to my local density of states. So they already have a relation between my density of states and my density-density correlations. So you need to put in some assumptions. So say that my density correlations decay like some way, and I put a tilde here because I isolated on the part where I have the specific wave factor, because I had some wave factor, right? Before I had the m point or the k point or this 0.5 or this 1/3, 1/4. Doesn't really matter. At some point, you can just extract the momentum dependence, and you have a exponential tail in 2D, which is 1 over r as well. And the major assumption about the local density of states is that I say, well, at long distances, the local density of states in these metastable states, they become just the density of states of my whole system, but cut off at this minus v over r, which is the stability requirement. So if I just say my local density of states is at long distance is roughly the same as the density of states of the total system with this stability cutoff, then I get a very nice relation between the density correlations and the gap at small energies. And you can relate it like this. So for a system with short-range density correlations, the gap will scale as exponential times the interaction energy divided by the correlation length and the absolute value of the energy. So that's the theory, and you can actually see that I plotted, or I measured in Monte Carlo the density of states for various types of interactions, or interaction strength, I should say. And the solid lines, yes, solid lines are the ones that I got out of the experiments, the numerical experiments, and the dotted lines are the fits to that. And there's a very nice fit that I put in the interaction strength, which I put here, and this is the one that the parameter that I get when I fit the measured density of states, and I indeed see this linear behavior. So at least on this level, I see some agreement with this idea how the density of states is related to the density correlations. So with that, I come to an end. I hope you recognize that throughout the talk, I discussed the system as a wild energy landscape. We see with Monte Carlo that it has slow dynamics. We have short-range correlations, which we also found from Monte Carlo, and a soft excitation gap. And I just discussed the theory that relates these two. In general, there's a lot of things to be done about Glassy physics, and I don't think there's one agreement about theory that necessarily relates how slow dynamics are per se, how you compute slow dynamics based on the landscape, or how you get the landscape related to short-range correlations, or this guy to this guy. So I think there's a lot of interesting things to be done, and I thank you for your attention.